Thank you, Tim, for the kind introduction, and thanks for coming here to introduce me. So today, in 7 minutes, I'm going to take you through one big aspect of the research, that is self-healing materials. So the first question I think should be asked is, what materials do you wish were self-healing? Um, as human beings, we break awful lot of things. Going back to our childhood, I'm sure you remember the toys that you treasured and then broke. And as an adult, we just break more expensive things like laptops and cell phones. But do things necessarily have to break, right? So self-healing is a type of approach in making materials where these materials can heal themselves or fix themselves on its own. So on the other side, we want things that are more catastrophic to be self-healing. For instance, structural damage in aircraft. So we definitely don't want the windshield or the body part of the plane to be broken up in the air, right? So we definitely don't want that to happen when you're on the plane. But one of the challenge with these systems is that the damage is very hard to detect. So it could be happening somewhere in the fiber composite panel in the wings, and it can be happening in real time as the airplane is stressed. And there is no way to prevent that unless these damages can detect itself that it's broken, and it can heal itself as it's happening and repairs it. So for these systems, there cannot be a human intervention. It has to be autonomous. And that is one of the design challenges for self-healing materials. And being part of the Center for Biodesign Center for Sustainable Macromolecular Materials and Manufacturing, our research is naturally motivated by sustainability. For the past 20 plus years, we've been told to recycle plastics, but even now, then our recycling rate is fairly low. I believe about 20 or 25%. So you can think of self-healing as another way of recycling, or even better. So where the material, we can extend the lifetime of these materials. And the impact for these is that you can really slow down the deposition of the plastic waste in landfills. And we can also consume less of the petroleum that is used to make plastic materials. So how do we do that, right? So when you turn to nature and you see that nature uses self-healing for a variety of tissues, whether it is soft tissues like skins or hard tissues like bones, and they can self-heal these functions, whether it's small scratches or it's growing out new limbs from broken arm. And this is what allows the functions to be maintained over a long time, right? So as a chemist and material scientist, we want to learn the principles that drive the self-healing in biological systems and apply these concepts in making materials and how we can make materials to have those functions. So in biological systems, you typically start with some type of wound, and it recognizes it, and then it's followed by some type of inflammatory response and remodeling to heal those damaged spots. In synthetic systems, we have to reimagine these steps and apply the concepts. So there's some type of damage in your material. So here I'm showing some type of polymer networks. And the damage has to lead to some type of trigger to bring about some physical or chemical response in the materials. And these polymer chains can reorganize and make it into a new material, right? So how do we do that? And there are other critical parameters to think about in making these materials. So in biological systems, the self-healing is occurring in like around water and at body temperature. But that's not really the case for the materials, right? We have a variety of applications. So we have to think about the kinetics of the fixing or self-healing. Hopefully they're fast. You don't want it to be too slow. You also have to think about the temperature that you want these systems to be self-healing, as well as the transport. So there's a lot of different parameters to think about. So typically when you make these self-healing materials, you do need some type of reversible bonds that can reform after it's been broken. So when you think about reversible bonds, like hydrogen bonds are reversible, ionic bonds are reversible. So these are all types of non-covalent interactions. These tend to be a lot weaker than covalent interactions. And because you're using these weaker bonds to make these materials tend to have a very low stiffness of Young's moduli in like a megapascals at max. So that kind of limits the applications of self-healing materials that's been demonstrated thus far. So one way to make these dynamic bonding interactions a lot stronger, it's bio-inspired, is without compromising that dynamic properties, you can introduce that multivalency in bonding interactions to make the binding affinity to be a lot higher than the underlying monovalent interactions. So these kind of interactions are abundant in biological systems, whether it's DNA, RNA interaction with proteins or protein-protein interactions, or even like oxygen binding to hemoglobins. So the reason why these weak bonds are a lot stronger is through these positive cooperative interactions. And you can introduce that concept in these polymers. One way to do that is by introducing nanoparticles, where you're assembling polymers and nanoparticles together. And because nanoparticle has a larger surface area, you can have like that multivalency in polymer networks. So that's the approach that we have taken to make these self-healing materials to have a lot higher binding interactions, so that we can solve this trade-off that we are seeing with these self-healing materials that's been synthesized thus far. So most of the previous methods in assembling self-healing composite materials is that they either attach nanoparticles or polymers directly onto the nanoparticles. But these methods don't really allow you to control the number of binding events. But we think that is one of the important parameters to control for polymer nanocomposites. So instead of relying on like directly attaching these polymers onto nanoparticle surface, we want to detach the core of the nanoparticles from the interactions. So we functionalize these nanoparticles with short ligands that has binding moiety at the end of those ligands. I'm scared to click. Oh, laser pointer. Interactions, and we want to tune the number of binding events between the polymers and nanoparticles at the interface. And some of the preliminary results demonstrate that this is very important in controlling the bulk properties. So the first step that we took was using a non-dynamic polymer that doesn't have any non-covalent interactions. It's a linear polymer. But by adding these nanoparticles that are functionalized with short ligands with carboxylic acids, we are introducing that non-covalent hydrogen bonding interactions between polymers and nanoparticles. So as a demonstration, these polymers alone without nanoparticles don't have self-healing ability. But by adding these nanoparticles, now you can self-heal these materials. And of course, we have to prove that it is due to that interfacial engineering. So we also functionalize nanoparticles with dodecaine thiol, which is not able to form that hydrogen bonding interactions. And we see that these are not self-healing. And we also don't see the change in glass transition temperature. So this is one of the bulk properties that people analyze using these polymers. So when you have those interactions, the glass transition temperature doesn't change. But when you have these nanoparticles with the carboxylic acids, we do see an increase in glass transition temperature. So hopefully I didn't go too much over in time, but so this is something that we've been working on. I didn't include any of those ACS conference because I was only given 7 minutes. But we have a lot of exciting things happening in my group, but also as a center. It's been a really fun ride for the past 2.5 years. This is my group, and thank you for listening. And I appreciate the support coming from Biodesign Institute.